All right, guys, we got a great video for you today, and you may have seen the Joel telling through the 3D printing nerd video where he got our 22 IDEX V3, this thing right here in the back, and he went ahead and did his first foray into the world of high temperature engineering materials.
High temp printing is still completely foreign to most of us, including me.
And he got pretty decent results for just using baseline profiles and old materials and not having the full setup, or just really being the first time diving into printing high temp, because it is very different. When you're printing PLA and PETG and other basic materials, these materials are considered basic because of the way they flow and the way the rheology behaves, which is the molten behavior of plastics and different things. And they became the standard because they're easy to print, which means using the printers was easier and more people could adopt using the printers. Then you get into the limitations like temperature. If you take a PLA part, for the most part, and you leave it on your dashboard in your car, it might droop and melt throughout the day on a hot day. So the need was born for more robust materials, engineering grade materials, high temperature, high strength, chemical resistance, radiation resistance, and things like that. Now here at Vision Miner, that's what we've been doing since 2017. That's been our bread and butter and complete focus. High temp, functional 3D printing. So we sell machines, we sell all the materials, we manufacture our own machine, and we make a bunch of different tools to make it easier for our customers. We also provide the training and content videos like this to show you how we do it. So today we're gonna dive into the prints that Joel did and see where he had problems and what we did to go and print the exact same part in the exact same materials and make them beautiful and perfect. If you haven't seen that video, there's a link in the description. Definitely go check it out. Much thanks to Joel. Always a good time. All right, so let's dive right in and start on the parts. First off, the part is this model by Clogs 3D, and it is basically just a C-clamp that Joel decided to print in a difficult orientation, kind of a torture test orientation, which is flat like that. So printed like this. As you can see here, we've got a couple difficult features. First off, this whole area is overhangs. This whole area is overhangs. All this stuff in here is overhang. And then you have tolerance tests where this is a free moving part within the larger part. So you gotta really have good dialed in tolerances, flow rate, extrusion, etc. Your temperatures have to be good so it doesn't just go melty all over the place. And you have to hit that fine line of just right for the layer height, temperature, everything else, cooling, etc. to get a beautiful part. And it's different slightly for every material. And generally in high temp, that also changes per part and per geometry, just slightly. Basically, the long and short is every time you print a model in a high temp material with a baseline profile, you got about a 50-50 chance of it working perfectly. And if it doesn't, there'll be some basic settings changes that you need to do to get it to work and give you the desired result. And that process is just knowing what settings to sort of start playing with as you go along. And then once you've got the part dialed in and it's working and printing good the way you want it, you can print over and over and over nonstop for as long as you need to. All right, so this is the part in our slicer. We're using Prusa slicer because it's constantly updated. It has great features and it's a very powerful software. You can use just about any slicer that you want with the 22 IDEX V3. It is a RepRap firmware-based machine on a Duet 3 board. So we've got our model, obviously plenty of challenges with this one. You've got all these overhangs in here. You've got this overhang here. The threaded overhangs, which are practically, I don't know what degree that is, but that's almost like 15 or 20 degrees. So those are very difficult overhangs to do without support material, as Joel did. So we're not going to use any support material today, and we're just going to tune this in for what it is. All right, so I'm going to go up here and let's choose Thermax PEI 9085, and let's hit slice. So let's check out the baseline settings that are going on here. It looks like we've got some interesting features. So from the bottom, it's going up immediately. You have overhangs, and then you have where the screw is beginning to generate right here. So this is coming up through here. Now, all of this area has to be spot on so that the clamp and the screw don't fuse, so that once it's printed, you can actually rotate the screw freely and have a working, functional print-in-place clamp. All right, going up to there. Now, if we were to print this for an industrial application in one of these materials, actually, you wouldn't print it in this orientation. You'd probably end up doing something more like this, where it would print flat, but we would redesign the model so that this clamp part was also flat, and then you would have all the layers in an orientation where they are the strongest, which is basically almost always horizontal. We've got really good at getting good layer adhesion, but it's still never quite 100%. Even on things like PCTG, it's at like 97.8%. So generally, if you can print it horizontal for the mechanical stress that's going through the part, you should do that. We're gonna start with Ultem 9085. This is the final version of the Ultem 9085 clamp, and it turned out beautifully. We do have a little bit of not perfect overhangs there, which is to be expected using no support material. But overall, there's no post-processing on this. We didn't pull supports, we didn't sand this. This is as it came off the printer. So you can see the worst part of this print is those overhangs, and frankly, that ain't all too bad. Let's dive right in and check out the first version of the part that we printed in 9085 on that 22 IDEX. So we got V1. Not looking too bad here. Now, what we did to print this small section of the part, which is actually a critical component, I wanted to show you guys this. So what we do when we're tuning a larger part, and we don't want to waste a bunch of filament printing the whole thing every time, or waste time printing the whole thing every time, is we'll go right into here, into the Prusa Slicer tools, and say, I know I don't want to print the whole thing, I just want to see what this area comes out like. I can go right here and click the cut tool. Now this gives me this whole thing that I can move up or down. I can give it different angles or whatever, and I can slice the part into sections very easily and very quickly. So let's just say I want to print just like this. Then you can say perform cut, and I'm going to get rid of object A, the top part. So I'm going to perform cut and leave it in the orientation that it was. Now I can do another cut and say we only want to focus on the area where the spring or where the screw is connecting. So I'm going to cut it here too, and we're going to keep object B, perform cut. All right, now I've got a smaller version of my part in actual scale that I can use to tune in superfine settings, but do it quickly and rapidly iterate the changes that I'm making and see the results before I go and use my filament to print the whole part. So really, really handy there. Something you really want to do. So let's bring this part back, Control Z a bunch of times. All right, so we've got the first version, and let's grab the second version here, just on deck. So between these, we didn't change the build plate temperature, we didn't change the chamber temperature, but we did change the layer height and the temperature of the nozzle. So on this first one, it's looking a little bit melty. It's definitely, you can see the layer lines and whatnot. But we went ahead and let's see version 2, where we changed that layer height and that temperature, and we can see this part looks a lot rougher just in general, and that's the layer height. That's the 0.2 millimeter, 200 micron layer height. Whereas this one, everything looks a little smoother, it just looks a little cleaner, everything's just a little more beautiful, and the layer height had a major effect on the overhangs. All right, so that's the difference. So we do a lot of printing in 9085 on this machine, and frankly, we were looking at Joel's part and we're like, why is this just look so terrible? And we think that it was wet filament and the drying process. Having that really good drying process, he did have the vacuum chamber, doesn't have an oven. Drying these materials is so critical. If your material isn't dry, what happens if your material is not like bone dry?
We have artifacts like stringing and blobbing and burn marks, certainly.
Stringing, blobbing, burn marks, it's just not going to be a good time. You gotta start with a solid foundation of extremely dry filament. Otherwise, you're just not gonna get great results. And if you keep banging your head against the wall wondering why your parts aren't coming out great, always go back to, am I really thoroughly drying my filament enough before every single print? Almost all of them have sat in the warehouse for a little bit before they got bagged up, and that means they absorbed a little bit of moisture. I believe Aeon 3D actually has their Ready Print line of filaments, which is dried right before it's put in the bag, so those are supposed to work great right out of the box. But other than that, we've found you just gotta dry it, no matter what. That's just the way it is. So, since we print so much 9085, there wasn't much more that we could do to this to make it better. And so we printed the whole thing, and we called that a success. All right, so we got our final part. So let me just show you real quick in the slicer how to do this, changing the nozzle temperature and the layer height. These are the only two things we changed. So let me just show you where you find that. Firstly, you have your part in here, and you go to print settings, then layers and perimeters, you'll set your layer height right here. Now you notice if I hit the back arrow, it defaults back to 0.2, and that's what the profile is set up as. So if you change it, you can just go to a different setting, and then it actually has a little call out here that's cool that tells you, hey, this has been changed from the default. So just make note of that. And then for temperature, we're actually going to go into filaments, and we've got the Thermax PEI 9085 set here, and we can set the temperatures right down here. So as you can see, default is set to 390, and if we went down to 370 for the first layer or other layers, you can set that. Now sometimes setting the first layer a little bit hotter can be beneficial to get that first layer welded down to the build plate with your nanopolymer adhesive underneath that, and but it's not always necessary. And usually in these high temp materials, it's not necessarily necessary. I like to use an extra wide first layer and a little bit taller. Use 150% of my layer height for the first layer, and you can do a couple degrees hotter if you want. I usually don't. So we've got our 9085. Let's go on to the PSU part. Now this is a part that Joel did not get working well. Let's dive in and make it work. So you can see here, we've got our final part. It's looking absolutely beautiful. When we were looking at Joel's print, really it was looking like probably the filament wasn't dry enough. And it was also very old filament from a different manufacturer that we sent him, what, 5-6 years ago? So with those factors combined, printing on our tried and true 3DX Tech PSU, which is what we sell at visionminer.com/materials, that is what we did here, and it came out beautifully, but not on the first go. So let's dive into the settings and see what we had to change throughout the process. Let's see, we've got V1, V2, and V3 for this one. So let's pull out V1 and check it out. You can see it's a little bit rough around the edges, and on the threads up here we've got some contamination, just a little bit. So it was the same thing here. We were starting at 380, 160 on the bed, 90 in the chamber, and a 0.2 millimeter layer height. It looks like the guys went and just said, hey, you know what? Let's go down in layer height to make these overhangs even better on that screw. Go down to 0.12 millimeter. Now, why not 0.1, you might ask? Well, on the 22 IDEX V3, the stepper drivers and the lead screw and all these ratios come together to where you really want to slice in 0.04 layer height increments. So you can see 0.12, 0.16, 0.2, 0.24, and so on. So here, we have version number 2. So as you can see right in here, you can see there's little pieces of contamination, and that's not good. We want a clean part without extra stuff in it. A lot of the time, PSUs use it for medical devices or electronics enclosures and things of that nature. And in a medical situation especially, you want to have a clean part. Now, it's not going to be like germs per se. This is going through a 380 Celsius nozzle. It's going to destroy anything in there, but it is carbon, and it is ugly, and it is not a beautiful end-use perfect part, which is what we want to get to with these printers. So we can see that there's a little bit of stringing, so maybe they dried it a little bit more. The biggest point on here was they switched over to a brass nozzle. Now, why would you want to do that? Well, you want to use a hardened steel nozzle when you're doing anything composite, glass fiber, carbon fiber, even glow in the dark, even white pigmented filaments with titanium dioxide will wear out the nozzle. So if you got a 0.4 millimeter nozzle, gradually as you print 500 grams to a kilo of the filled carbon material, you're going to end up with a hole that's about 0.5 millimeters, not 0.4 millimeters. And over time, that'll begin to affect the quality of the print, the quality of the parts, the overhangs, the walls, the surface finish. You'll be able to see it in the actual part over time. So using hardened steel that we sell at visionminer.com/nozzles, it'll fit all the E3D V6 style hot ends. It's a very standard nozzle type. And using the hardened steel lasts a very long time. I don't know if we've successfully worn out our hardened steel nozzles here in the shop. Now we do opt to go for a fresh clean nozzle on a lot of the print jobs we do, just because that's the best way to eliminate and get rid of any chance of carbon and contaminants like in this part. But switching to a brass nozzle is actually going to improve the thermal transfer. So the amount of heat and how it transfers heat from the nozzle to the part, or just from the hot end to the tip of the nozzle, brass has a better transfer of heat. It's more conductive, thermally conductive than hardened steel. So a lot of the times when we're printing in hardened steel nozzles, we actually crank the temperature 10 to 15 to 20 degrees centigrade just to make sure we're pumping enough heat through the nozzle for the speeds we're printing at and the material we're using. So they switched over to a brass nozzle, still at 380 Celsius, and down in layer height to 0.12. And then for this next version, it looks actually, everything is exactly the same. So V3, they went for the full print, the full build, and it came out, and it's functional, and it twists really, really well. It's definitely like working, but there's all this contamination, all this junk. Okay, so this was a brass nozzle on that hot end, which had previously been printing TPU, thermoplastic urethanes, flexible materials at low temperatures, like 240 to 280, really. So what happened there is, even though it was cleaned out and you push the material through it, there's still occasionally some carbon buildup and whatnot inside that filament path of the hot end, and so it picked that up and deposited it throughout the part as the print went along. Now we don't want to do that, we want to avoid that, and so they actually wanted to avoid contaminants and any chance of burning or being a little bit too hot. It's a pretty simple part, and so they took the temperature down as well, down to 350 Celsius, left everything else the same, and printed this beautiful, fantastic, fully rotational, functional PSU C-clamp. Now, as you can see in this part, there is still some contamination, but sometimes that's burning. And a lot of the times, we'll print these in arrays, because we don't just need one part, we need 10 or 20 or 100. So a lot of the time, keeping that part temperature down can help, but just being on one part, all that thermal mass, really just doesn't help. So, this is also another reason it's important to do the scheduled and continuous maintenance on your machine, like cleaning the rails, lubricating the rails, just cleaning your machine out. These contaminants could be contaminants on the filament spool itself, like just little hairs and whatnot that are, dust that falls out of the air onto your filament, and then it runs all the way through the machine, and then it comes out the nozzle, gives you a little black spot. It could be dust that's inside the machine, maybe floating around, and it landed on the part and just hit that temperature, poof, turned into a little black carbonized dot. There's a lot of different factors for this, but the more dialed in and tuned in your process is, from the drying process to the actual printing and tuning process, the better results you're gonna get. Now, the other prints that Joel did turned out actually pretty well. So we didn't do all of them. His PCABS part with no tuning on an ABS profile came out beautifully, and his glass fiber PEEK part came out also very nice. So we didn't feel the need to do those, but we wanted to introduce two other materials and just throw these in real quick. Here we've got CFPEEK Gen 3 from 3DX Tech. Now it's a 10 to 15% carbon filled nylon 6, and we've also got Ultem 1010, or Thermax PEI, made from Ultem 1010 trademark. By the way, the whole thing on Ultem, guys, Ultem is the trade name for PEI, which is polyether imide. Now there's many different grades of this, but the trademark name is owned by SABIC, even though it was originally developed by General Electric, I believe. So let's talk about the Carbon Fiber Nylon 6 version real quick. I have no data, I have no charts and graphs of what was changed, because they used their stock profile and printed it out, and it came out perfect the first time. So as you can see, highly functional, very much works. So an interesting thing happened. As you can see here, we've got a matte finish on the part. But then as soon as you get up here to this very top part, it turns shiny. Now that's indicative of overheating or just being really hot. Really what's happening there is, if it prints in this orientation here, it's moving the head from here to 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 here until it gets here. Now, as it's printing this side's cooling down. And then it moves over and it's printing this and this side's cooling down. Once that stops and you get past this top part here and you're only printing this area, now all of a sudden you're printing layer after layer after layer on the same part of the part, and you're getting thermal mass. The part is soaking up the heat, hanging out of the heat, and it doesn't have enough time to cool down, which means it's just staying really hot, which really gives you good layer welding. Really, really good. Now this can be a problem if it gets too melty and then it turns into a gloopy blob, as many of you I'm sure are familiar with. But here it's kind of cool because that section of the part is going to be isotropic strength. Kind of a cool little feature. But let's check out the actual strength. With the stock profile on the Gen 3 PA6, we've got a broken part. So as you can see, we broke it. We like to break things here. Leave a comment down below if you remember all the flames and breaking parts. If you want to see more of that as we're doing all these videos on Filament and the 22 IDEX, let me know in the comments below. Should we burn it? Should we melt it in chemicals? Should we break it? Is there a different type of breaking we should do? Anyway, let us know what you want to see. We got a lot of stuff coming. But right here, you'll see we broke it, and it broke pretty darn good. Now by good, what am I looking at that makes me determine this had good layer adhesion? All right, so what you'll see here is you can see the infill, which is the open areas, and then you'll see the perimeter, which is that solid border outline. Now what you're noticing is that this did not break along layer lines. I don't see any stray layer lines. I just see jagged breaks. So you can see it's breaking up and down and all around, which means that the layers were adhered very together, almost isotropic. This is almost like an injection molded part where the layer adhesion is so good that it doesn't necessarily break along that layer weld. It's breaking as if it were a solid piece of material, and that's what you want to see. So if you're considering a printer for any kind of CF nylon, CF polycarbonate, or anything like that, and you need bigger parts, then this machine's amazing because you can get the entire chamber up to the right temperature to where the whole part is an optimal temperature for that next layer to be welded on, and you just get way stronger parts, especially with something like this where you have 100 Celsius in that chamber. Well, here, I'll just break this on camera real quick. Let's do an easy break. I'll screw this down. Sorry, Manuel, I'm gonna break it apart. And, oh yeah. All right, here we go. So again, we can see right in here, it's not breaking on the layer lines. In fact, hopefully you can see in there that it broke and it jags up and down through the layers, which is ideal when you have a part like this. So, pretty darn good results printing in CFPEEK with the stock settings. That one was a success. Next, we've got Ultem 1010. Now this is a beautiful material, highly used in aerospace, also heavily used in high voltage applications. This stuff will take a lot of energy. It's very insulative and can be used in solar panels or extremely high voltage applications. It's also highly chemical resistant, extremely rigid, and quite difficult to print sometimes, depending on your geometry. Ultem 1010 is one of those ones where you can get amazing, beautiful parts. What you want to do is make sure that your wall thickness isn't too much. We printed very large objects with very thin walls, and that works great, but if you get too thick, it just doesn't adhere, and it just starts breaking apart from itself. So that's one of the things. Let's go into that for a second. Limitations in high-temp materials. We saw some comments on Joel's video and some of our own videos talking about how you can print tiny parts, but not large parts, and it's really a combination of wall thickness and size. So these materials require a heated chamber because if they don't have one, they warp up like crazy. Now, for Ultem 1010, you really want a chamber temperature of like 230 Celsius for the best possible results. Just below its glass transition point, right around that area, so that you get really good layer adhesion and layer welding, and the whole part stays hot during the print, so then when you take it out, it all cools. But then you do have a lot of internal stresses where annealing comes in. The only issue with annealing is a lot of the times when it relaxes those stresses, the part will shift itself and your dimensional accuracy goes out the window. So at Vision Miner, we always like to not anneal if possible, just to maintain that dimensional accuracy and print as strong as possible. And if it's a semi-crystalline material, to crystallize it in situ during the printing process as opposed to annealing later, because with the crystallines, it gets even more out of whack when you get into annealing. So with this machine and these materials, you are limited to a certain extent, but it's mostly about wall thickness. If I wanted to print this in solid Ultem 1010, we could probably get a 2" by 2" or maybe even a 3" by 3" cube before it just starts warping so much and crazy failing. But then, if you're printing 100% solid, you have another problem. Even on the machines that we sell, like the Aeon 3D high-low machine with the 250 Celsius chamber. If I want to print a 3x3x3 block, 100% infill, solid, you still can't quite do it. Because what happens in that situation is you have so much hot material in this part, you have so much that it hangs on to the thermal mass. Without the proper cooling, okay, let me take that back, the high-low could probably do it, because they have cooling jets. It's a really cool new technology. If you want to know more about the high-low and you're doing big Ultem parts in aerospace materials, give us a call, shoot us an email. We are here to help you with that. But on these machines, when you're printing that block, it has so much thermal mass that it hangs on to that you just end up with a big melty blob inside of the actual part. So you might get the perimeters, but the inside of the part is all out of whack. So 98% infill is much more effective. Just enough space in between all the extrusions to let it cool appropriately and get that solid block. But then it's not solid. So in these materials in general, there's limitations. It's a very different world from your PETGs and your PLAs and your ABSs. But on a machine like this with a 100 Celsius chamber, you can get away with a lot. And the main benefit of this type of machine is 80+% of the parts that we've seen come through our print service and on the market and from our customers fit within that smaller profile so that you can actually do the parts that are being produced. Now, that's one that's actually boggled my mind too. Why are all the parts in these materials generally small in actual industrial use cases? Well, they're also very hard to machine on a CNC, because if you're hitting it with a cutting tool at really fast speeds, then it's heating up the part and the material warps. So CNC, all right, also difficult. What about injection molding? Okay, you can do a lot with injection molding, but once again, especially with materials like PEEK that are crystalline, you have to have that mold so hot, and then you have to inject all that material so hot, and then cool it down at the right speeds to get the good part that's not warping out of control. Again, very difficult. And that's where 3D printing comes in, making all this stuff much more possible. It's opening up realms of parts that could not be done before because they can do them additively. So no matter which way you look at it, if you're somebody that's using Ultem 1010 for your parts, you're probably having a hard time with it. And that's where we come in. We can help you get one of these machines, get the right materials, and get set up and running, producing your own parts in-house. So let's dive into the settings that were changed for this Ultem part. Right here, we've got the temperature. Looks like we went down and then back up. The build plate temperature, we went up. The chamber stayed the same at 90. The layer height, we automatically started out at 0.12 and just kept that the same. And the volumetric flow we kept at 5. But there was one different thing that was changed in this, and that's the speed of 30 millimeters a second. Now, let me dive in and show you how we set speed on this machine and what the difference is here. So I'll go into Prusa Slicer, I'll go into print settings, speed right here, and then we see this speed, 50 millimeters a second, but that doesn't actually do anything right now. I want to scroll down to the bottom and look at the max volumetric speed along with the max print speed. So the max print speed is what it sounds like. That's the maximum speed that it will print at. And the volumetric flow is going to be calculating that per layer, it's going to try to keep it flowing the same amount of material throughout every layer. So we can set that to, it's set to 6 here by default. And let's slice that real quick and then look at speeds. So in Prusa Slicer, I can go up here and go actual speed. Now we see that the green is all about 20 to 30 millimeters a second, whereas the yellow is about 50 to 60 millimeters a second. So throughout the part, it's printing at different speeds as it goes along. Now let's just go change this to a 4 and see what happens. So now we've got the orange, which is like the orange and yellow is 44 to 51. The bright green is around 22. And any of the blues and anything we see here is around 7 to 14. So massive change. Let's go to 22. Let's just see what happens. Slice it one more time. A lot more flow. Now we've got the yellows around 50 to 60 and the greens are at 30 to 40. So let's go in and actually change this up top, the parameters, to say 100. See what that does. Okay, so now we see more red in here where it's actually going 100 millimeters a second. There's a big differential in some of those parameters. Sometimes going like the Wild West off of experience just works. And our experience, starting back in 2017 with the FunMat HT, was print at 30 millimeters a second, everything. And it usually gets a pretty good result. That was a baseline profile. So what the guys did, just to test out some different stuff, was they set everything up in this section to 30 millimeters a second, 30 millimeters a second, 30 millimeters a second, 30, 30, 30, and 30, and 30. There's no support, so it doesn't matter. And slower for the, or 30 for the bridges and the everything. 30 for bridges, 30 for gap fill. So everything is set to 30. Let's see what that comes out like. Actual speed, now it does slow down to 15 for some of these edges and perimeters at the corners here, you can see. But for the most part, the entire part is printing at about 30 millimeters a second. So with those settings, we went in and just basically adjusted temperature. So let's look at that now. So we've got our final part. Let's look at revision 1. I mean, frankly, this is pretty beautiful. So Nazar came in and was like, hey, let's see what happens at a lower temperature. And that produced revision number 2. Again, beautiful, but I see something. I see something very significant. Let me turn it this way. So, you know how earlier I was talking about how Ultem, when printed too thick, 1010, specifically Ultem 1010, when printed too thick, can break apart from itself. Well, if you look right here on this part, we see it is cracking away from itself. Now this is Rev 2, basically turn the temperature down, which is gonna lower the amount of layer adhesion because you don't have as much heat to then melt the below layer, and so you don't get as good layer adhesion. So we see that happening down here in the form of a crack. Right there, you can see that's the part literally warping away from itself. It's like, yeah, we're good. No, I had too much internal stress. Oh, dude, it's crazy. I've seen this happen on much bigger parts, and then you're like, oh dear Lord. So what do? They raise the temperature back up for revision 3, and they also raised the bed temperature. So instead of printing at 160 Celsius, they bumped that up to 180 Celsius. And here we have revision 3, looking beautiful, fantastic. So here we have a third version at 380 on the nozzle, 180 on the bed, 90 in the chamber, and 0.12 on the layer height. Volumetric flow of 5, and all the speeds locked out at 30 millimeters a second. And with that, they said, all right, that's good enough for this video. Let's print the whole thing out, and we got our beautiful final part. You know, one of the discussions around the office is what type of sample parts should we send potential customers? So let me know in the comments down below, what would be a good sample part? A clamp is kind of cool. We could do bottle openers. We could do pens. I really want to print some transparent Ultem 1010 pens, like, you know, those ones that are like bolt action. That'd be super cool. But let me know if you got some ideas down below, and we'll make a video on it if we feature your idea. All right, guys, we're back in the studio. It's actually a couple days later, but I had to jump back in because Manuel was like, Rob, did you finish filming the video? And I was like, yeah, why? He said, well, I finished the Carbon Fiber PEEK one. So I'm like, wow, we gotta put that in there. Let's check this thing out and go through exactly what it took to get here, because you can see over here, there are several revisions. So let's look at this first one. Let's check this out. So as you can tell, this did not go as planned. It's kind of cool looking, kind of like abstract art or something like that. You can see the Hilbert curve infill inside there. By the way, Hilbert curve infill is a very good way to get rid of internal stresses in normal infill. It's not the best way to give your part the most strength, but for high temp polymers like Ultems or PEEKs that warp a lot, if your part isn't taking a ton of mechanical strength or that's not the primary application for it, using the Hilbert curve in Prusa Slicer is a very good method to reduce the warping. Use Hilbert curve when you got really warpy parts that don't need a lot of mechanical strength. So clearly we can see we've got pitting in this area. It just looks horrible, and it printed like that. So you can tell at a certain point this started happening. Wait, oh, this is a different one. This is 2 different revisions that got clogged. Oh yeah, 2 different revisions right there. This one I would say probably happened first, and maybe this one second. So what'll happen is you start your print, everything's looking beautiful, first layer goes down great, and then about 20, 30, 40, 50, an hour into the print, you get a nozzle clog. It's kind of hard to predict, which is why in our print service we use a fresh nozzle every single time. Sometimes it's the heat break, maybe 10, 15% of the time, but most of the time it's a nozzle. So if you start seeing under extrusion, there's a good chance there's something occluding the nozzle, preventing it from having the full flow. So you want to check on that. So that was the first run. We've been printing a lot of stuff, a lot of different materials. All right, looks like it's time to change the nozzle. So we went to the second revision, and long story short, same thing happened. As you can see, we have a very porous part. Definitely not good, but you can see right in there, it was decent, but then it just got up to there. And you walk away from the printer, 30 minutes later, you come back to this. Clearly, time to stop the machine and reassess. So, again, part of the process. If you buy a 22 IDEX and you're printing these advanced materials, to get your part dialed in, sometimes it's gonna take this type of work. Sometimes it works right out the gate, which is great, but most of the time, you do a little bit of pre-work and then you have your part. So, they also, on that second revision, turned the temperature up to 420 degrees, just in case, using that hardened steel nozzle with the high temperature peak. 400 is kind of low, and when you're using hardened steel nozzles, you want to up the temperature 10 to 15 degrees Celsius because it's not as good with the thermal conductivity. So not as much heat is getting from the hot block down to the tip of the nozzle. So you want to up the temperatures a little bit. So they tried it again at 420, still jammed, didn't quite work. So the next revision, they went up to 430, and they also increased the layer height to 0.2 from 0.12. Now, this is kind of important sometimes with carbon fiber or glass fiber, anything filled composites, because it's less space for that material and those fibers and everything to come out of the nozzle. Now, we do have really good success, especially with the Carbon Fiber PEEK from 3D X-Tech, because they use aerospace grade carbon fiber compared to industrial grade, which is thinner strands that are more rigid. So it's just a finer material coming through the nozzle. You can get away with a lot more. Even a 0.2 millimeter nozzle can print the 3D X-Tech PEEK with carbon fiber. Now, they did this and it did successfully print. So let's check out the results. So 430 on the nozzle, 0.6, they also changed to a 0.6 nozzle with a 0.2 layer height. So they did a couple changes on this one, and it looks like it came out pretty darn good. Overall, see, it came out in that orientation. You know, with a 0.6 nozzle, another tip of the day, most of the time, going from a 0.4 to a 0.6 is negligible when it comes to fine details, but a massive difference when it comes to printing speed and strength of your part, because with a wider nozzle, you're laying down a wider path of plastic, so it's more solid plastic, which is just going to be stronger, and you go faster because it's more plastic getting laid down for the same part. So if you're laying down more plastic, the part's going to be done sooner. So another tip of the day, $50 tip for you. Use a larger nozzle. Things start to change a little more at 0.8 to 1 millimeter nozzle, but 0.6 is just a really good in between. So we've got a great part here. It looks good. The overhangs are decent. So this is an experiment. This is about tuning in to the same settings. It's not about switching to a better process, like a 0.6 nozzle and the higher layer height. It's about matching the 0.4 with the 0.12 layer height, and so that's what they're doing. So they got that out, but the quest continues, the journey goes on. We've got revision 4. Here we go. Oh, this is the one I broke. This is the one that Manuel brought back, and I was like, cool, looks great, but let's break it. Is it strong? Is this gonna work? So revision 4, temperatures are the same. The layer height went down from 0.2 to 0.6, and we went back to a 0.4 millimeter nozzle, and this is the result. Quite a beautiful result, if I do say. It looks very nice. Now let's actually compare that real quick to the 0.6. I wanna see the difference. Temperatures are the same, layer height's a little bit lower. This is the 0.6, this is the 0.4 nozzle. What you really tend to see is these corners are a little bit more rounded and these corners are a little bit more sharp, and that's because there's less walls over here and more material being slung around, and more walls here with less material being slung around. So a little bit of a difference, most of the time negligible. For your application in your business, you be the judge. Put this one back away. So overall, this part turned out great, but we don't care about it just looking good 90% of the time. We want it to be strong, we want it to be good, we want it to be robust and use that awesomeness that is polyether ether ketone with the carbon fiber embedded. So Rev 4, awesome. Let's do it some more and just keep chasing that perfect part. All right, so then we've got Rev 5. We're at mostly the same settings, but we had some interesting things happen down here at the bottom of the part. If you really look, there seems to be like some cracking or some occlusion or something, just missing material, possibly cracking, something down there going on that we're not entirely sure what it is, but it's not good, so we said print it again. So we'll print it again. And this time they changed the minimum shell thickness, which basically is a setting that tells you, hey, I want my walls to be at least 3 millimeters thick and I want at least 3 outlines. Now usually 3 outlines is not going to be anywhere close to 3 millimeters, so the slicer will automatically change the number of outlines or the thickness of the shell to be your desired value. So they set 1 millimeter on that, which slightly changed the G-code tool pathing and whatnot, and gave us this one. They printed it, it came out quite well, beautiful, but there was some suspicion of weakness and different kind of cracking. So Manuel comes to me with this beautifully printed part, says, hey, it's good, it's done. I said, all right, great. Let's break it. Is it really good? Is it really done? Is it actually strong? How's the layer adhesion? You can print a beautiful part with 0 layer adhesion, and is it really a good part? No. So, well, for some applications maybe, but let's look at where it broke specifically. So the top of the line there and right there. That looks pretty darn close. It's definitely not the same layer, but it's close enough, and it's breaking along the layers. And that means either your temperature's not high enough or some other reasons, but it's definitely not good layer adhesion. So I said, Manuel, what temperature are you printing at? And he said 430. I'm like, we print usually at 450. Why so much lower? It's like, really, when you print at lower temperatures, you get less oozing, you get less just drooping and things like that. And it's generally easier to get a pretty part. But what we found is your layer adhesion often suffers. Now, you don't want to print really slow, a lot hotter than the recommended temps for your polymer. But you can, especially if you're going faster. So some printers out there have been printing peak at 500, 600 Celsius, but they're going so fast at the peak, the polymer comes down through the melt zone, and then it's out of the melt zone before it actually gets up that high, which would be high enough to degrade the polymer. That's what you want to avoid. You don't want to degrade the polymer because you're heating it up too much. So for many years now, we printed at 450 Celsius. So I told him, hey, just bump it up, hardened steel nozzle, let's see what happens. It should be just fine. And so he did for Rev 7, much stronger, much better layer adhesion. And here we go. We've got good details around there. We've got good top layers. Let's look at the overhangs are pretty darn good there. It's just barely any. Again, this is with no support, guys. If you're doing this for a real project, you're gonna use support material. It worked without it, so very good. Absolutely gorgeous, very beautiful part. That is the Carbon Fiber PEEK version. Now, if you haven't already seen Joel Telling, the 3D Printing Nerd's video, printing these parts on the 22 IDEX, his first foray into high-temp 3D printing.
I do have access to some really cool materials.
And so we wanted to go in and show you how we make these parts really good. So if you haven't already seen that, link down in the description, go give it a watch, give it a like, give it a share. Great content over on Joel's channel. Cool, so anyway guys, I hope this video has been helpful. We're making more and more videos on tuning and printing all these industrial materials on the 22 IDEX V3 right over there. So if you're interested, if you're printing these materials or you need to print these materials, we are here to help you. We have been doing this since 2017. It's our bread and butter, and it's all about making it work for a good ROI, because time is money and business is about making money and putting food on the table for you and your family. So if you're into it, we're here to help. Give us a call, shoot us an email. We also have industrial 3D scanners, so you can do the full process of scan the part that you have no CAD for, turn it into a CAD file, and then slap that on your 3D printer in a functional material. We've got the whole lineup. So make sure you are subscribed, like this video. It helps us reach more people and get this information and this training and this education out to expand the industry as a whole. That's what we're here to do. We're here to get you on a 3D printer, making money, saving time. Anyway, thanks so much for watching. Have a positive rest of your day, and I'll see you on the next video.